average reaction rate and unique average reaction rate. In this video, we're going to be covering some definitions and a little bit of calculations. So we'll define average reaction rate, we'll define unique reaction rate, and then we'll calculate the average reaction rate, which isn't going to be that much different than calculating any average ever. So first off, let's talk about average reaction rate. And we're going to talk about this in terms of driving a car first, because it's better to kind of relate this to everyday life so it's not feeling like something totally new, because it really isn't. So if we want to figure out the rate of your drive to school this morning, we can look at your average distance and put that over your average time. Or if we're just looking at one drive, your drive to school over your time. So let's say you have a 4-mile drive to school. And I'm going to put it in terms of hours just because that's what we're used to looking at for speed of a car. So 0.047 hours. You would have driven 85 miles an hour. And that is your average rate to school. Now, notice that doesn't necessarily mean that you were driving 85 miles the entire way. Maybe the last mile you were driving 5 miles an hour, which means that you must have been driving well over 90 miles an hour on the previous part of it. It's just looking at it over the whole distance. And this is the same way when we look at average reaction rate. So the way that we define rate when we're talking about chemical equations is concentration over time. So just like with the rate of our car driving, it was distance over time. This is concentration over time. And it looks very similar. We still use the little triangle delta, but now we have a concentration of A. It's typically in molarity over our time, typically in seconds. Now we'll talk later about how we can measure this because there's several different ways. In this case, I showed it with changing colors, but there's lots of other ways that we can do it as well. Now let's look at something else that happens here. If we have something with two reactants, and two products, we can talk about this in several ways. We can take and look at the average rate of consumption of A or B, in this case our reactants, and say, well, how much does A change over time? How much does B change over time? Or we can look at it as in terms of rate of formation, and instead look at our products and say, well, how much of C do we make over time? And how much of D do we make over time? The problem with this is that these could all be different. If everything is a 1-to-1-to-1-to-1 ratio, well, they would all be the same. But that's not generally true when we're talking about equations. And so it would be nice if we just had one thing that we could talk about, that if we said the rate of the reaction is this, we would know what we were talking about. And that's what unique reaction rate is. So what we can do is we can normalize these based on the coefficients and divide the concentration over time by the stoichiometric coefficient, or the coefficient that is in front of the equation, the balanced chemical equation. Now, these should all be the same. If not, something else is going wrong. So the formation of C and D, when divided by their coefficients, should be the same as the consumption of A and B, when divided by their coefficients. And so we called this the unique average reaction rate, and it is a useful term to have. Now think back to our car example. We talked about how you could have been going way slower than 85 miles an hour at some points in the drive, and way faster at other points in the drive. This is going to be kind of true with our average reaction rates too. The average just looks at one particular time point, or one set of time points. It doesn't look at one point in time. So again, average reaction rate looks at a range from one point to another point, and it's only true during that particular area of time. But we need something that says, well, at this particular concentration, at this moment in time, what is my rate going to be? And we call that instantaneous reaction rate. And so if we look at this graph that we have up here, and take a minute to look at your axes, you have time and you have concentration. And as time goes on, the concentration gets lower. So we're talking about some reactant here. If we want to know a range, if we want to look at an average rate, we could pick any two times and we could look at the difference there and look at that little range. But maybe we want to know, well, if we give you this concentration of reactant, what is its rate going to be? And to get that, what we actually do is we look at the slope of the tangent of the curve. So that's drawn here at 2 different time points. And you can see that when the concentration is higher, the slope is much steeper. And when the concentration is lower, the slope is much lower. And that slope is what gives us our instantaneous reaction rate. So average reaction rate is a range, instantaneous reaction rate is 1 point. So we'll do a quick review on this. Average reaction rate is the change in concentration of a product or a reactant over time. Unique reaction rate is that average reaction rate that we're talking about divided by the coefficient from the balanced chemical equation. And then instantaneous reaction rate is the rate at one specific concentration. And this is found by taking the slope of the time versus concentration graph.